Okay, I'm recording now.
Well, hello everyone. Welcome to our virtual SI for October 29th. Today we will be going over energy and its applications in various circumstances, both with a pendulum, with a spring, dealing with friction, kinetic energy, potential energy, all of the above. So yeah, we'll go ahead and get started.
Okay, so for the first example, we have spring energy. So there's a 5 kilogram cube attached to a spring with a spring constant of 800 Newton meters, and it is compressed at a certain distance x. When the spring is released, it oscillates around its natural length, but all initial energy is entirely lost to friction by the fourth oscillation. Write an equation relating the initial compression length to the total distance traveled by the cube during its oscillations. Okay, so for this problem, we are looking at a cube that is moving back and forth, going past its natural length, compressing, expanding, and eventually by its fourth oscillation, it's going to lose all of its energy and stop completely. So I will move this over to the whiteboard so that we can do some of the work for this. Okay. So we have the cube, which is on a spring, and it is moving back and forth and oscillating until it loses all energy. The values that we know is that the box has a mass of 5 kilograms, that mu k is equal to 0.28, and that the spring constant is equal to 800. So when we're looking at this problem, Josh, do you think we're going to need to look at kinetic energy at all?
Well, kinetic energy does occur while it is moving, but looking back at the word problem, it talks about compression of a spring, which is elastic potential energy, so we definitely need to worry about that. And it talks about energy loss to friction. And it doesn't anywhere say there, or even in what the question is asking for, it doesn't ask us to find any sort of speed or anything about its movement. So I think for the most part, we can just look at the times where it's not moving, which would be when it's at its max compression or max stretch. And we don't actually have to look at the times where it's moving.
Right, so when it reaches its maximum distance before changing direction, it's actually stopped, meaning it has no velocity and therefore no kinetic energy. So in this case, we can just look at potential elastic energy and work due to friction. Okay, so even though there is motion, we are not going to use kinetic energy because at its final point, so it's moving back and forth, it's going left, right, and what we're looking at is the energy at the endpoints before it changes direction. At these points, the velocity is equal to 0. Therefore, there is no kinetic energy.
Another example would be, I'm going to simplify it a little bit. If we had a problem that was like, asking you if you're given a mass of something that's moving, and this problem is asking you to find its weight, right? You just multiply that by g. Like, even though it's moving, you don't need to really worry about the fact that it's moving. The kinetic energy has nothing to do with what you're actually trying to find. Like, and same with this example, the kinetic energy doesn't really have anything to do with what you're trying to find. We're trying to find an equation that relates the initial compression to the total distance traveled. We don't have nowhere in there to talk about speed, so we don't really need to bother ourselves with kinetic energy.
Yeah. So in the context of this problem, we can just solve using spring potential. So looking at the first oscillation, let's look at it oscillation by oscillation. We have potential spring energy, so UE of, let's call that 1 because it's the first oscillation, is going to be equal to the potential energy of the second oscillation, but in addition to the work lost due to friction. And the equation of work, if we remember, is that work is equal to force, so the friction force in this case, times distance. So we can make this the frictional force times the distance. Now looking at the second oscillation, so we would be doing the same thing. The potential energy of the second oscillation is going to be the same situation as the first. We're going to have the potential energy of the third oscillation in addition to the work lost in that oscillation. So every time it oscillates, it's losing more energy to friction. So this is going to be a pattern that continues for the rest of the oscillations. Do you have anything to add to that description, Josh?
I think that's good. What about avoiding a sign error?
So in this case, because we're using friction, which is a force which is always going to be resulting in a loss of energy, we don't need to worry about these forces being positive or negative. We know that friction is always going to be energy that is lost from whatever the initial energy. So you can see it's being added to the final and therefore it's being lost from the initial. So that's the way that that sign works.
Makes sense.
So again, this pattern will continue. Let me label these distances actually. So that'd be distance 1, distance 2, distance 3. So with every oscillation, it's going to lead to a certain amount of potential energy, minus or in addition to the energy loss due to the friction. So then fourth oscillation with the same thing. The only situation here is that we know that in the, sorry, that's 4. We know that in the fourth oscillation, it's lost all of its energy, so we can state that the potential energy here is equal to 0.
How do you know that?
So the problem stated that after 4 oscillations, it loses all of its energy. So we know that it has 0 potential energy for its 5th oscillation. So we can make the assumption that that is 0.
So if there's 0 potential energy from the spring, where would the block be located?
The block has stopped moving at that point, so it will have returned to its natural spring length.
Right, because that means it hasn't stretched or compressed at all.
Right.
Because otherwise there would be energy. But since there's none, it has to be stopped at the right where it's at its natural length.
Yeah, so using the equation 1/2 kx squared, we can say that x is 0 as it is no longer moving and it's returned to its original position. So given that, we now have these problems, but what the problem was asking for is an equation that relates distance to the energy and the force, basically. So there's a pattern I'm seeing here, which is that I can basically take the next equation and plug it into the previous. So in my first equation, for instance, I have potential energy of the second oscillation, and my next equation, I can plug that in. So if I take all of these equations and move them up, replacing my variables with the equations that I've written below them, I can simplify this into an equation which is my potential energy of the first oscillation is equal to my force of friction times d1 plus d2 plus d3 plus d4.
Is E1, is that the potential energy after its first movement, or is that its initial potential energy?
That would be its initial potential energy. So that would be the potential energy right before its first oscillation. Yeah. So yeah, that's the initial potential energy when the spring is compressed to distance x. So we have this value here. Another way of writing this would be as the frictional force times the sum of all of the distances. It's a simpler way of writing it. But this is the equation that we basically get down to, which gives us our energy in terms of friction and distance traveled. But what it was, yeah.
Looking back at the problem, it's relating the initial compression length to the total distance. So what would the next step be if we're relating energy to distance currently? How would we relate the initial compression length to the distance?
Okay, so there's still another step to go so that we can relate it to compression. I'm gonna clear my screen now so that there's more space to write. Okay, so we have the equation that we got was potential energy 1 is equal to the force times the sum of the distances. Now, we know that potential energy elastic is equal to 1/2 kx squared. And what is the frictional force equal to in terms of variables that we have, Josh?
Well, we know that the friction force is directly proportional to the normal force. And since we are on a flat surface, you know, the normal force must exactly counteract the force due to the weight. So the force due to the weight would be mg, right? And since that must also then be equal to the normal force, and then we just multiply that mg by our coefficient of friction, which I believe we were given.
Yes, so that is our equation for friction. So now plugging this back into the equation we already calculated, we get 1/2 kx squared is equal to mg. And we can rearrange that to solve for x. So we get x.
We also have the sum of d.
Right, times the sum of d. So we have that x would be equal to square root of 2 mu k mg sum of d divided by k. Okay, so that's just using algebra to rearrange using the equation we already have. So that would be the answer to part A, which just wants an equation relating the compression to the distance traveled and the energy.
Which part refers to the distance traveled?
So the sum of d would be the total distance traveled through all the oscillations.
Got it.
Okay. So now going back, what is d though? So at the moment we're just solving in terms of variables. So at the moment we are not actually looking at values for any of these. We're not able to calculate anything. But going back to the slide for a second, we're going to look at a part B for this problem. So okay. So there's a second part of this problem which says finding the initial compression length given the following value. Find the initial compression given the following values. So we have distance 1 is 3.2 meters, distance 2 is 1.7, distance 3 is 0.92, and distance 4 is 0.35. And you'll notice that the distances decrease as they go along, which makes sense considering that it should be losing energy as it continues to oscillate. So how would I use these values to solve for the compression, Josh?
Well, if we have our equation that we just calculated for part A, and we want to find how much it is initially compressed, and we know mu k, we know m, we know g, and I believe the only thing we didn't know was D, but now, well, I mean, we didn't know some of D. We now know all of the individual values for D. So if we just sum those together, we should be able to plug that in. Oh yeah, we also know K, and then solve for our X. So do we, when we're summing D, do we have to take into account the fact that the distances go different directions?
So in the case of this problem, we're not looking at displacement, like how much, whereas we would be looking at magnitude and what direction. We're looking at just actual distance traveled. So because friction is a lost energy no matter what direction it's traveling in, we can treat these distances as absolute values and just see the total distance traveled, because that would relate to the total amount of energy lost due to friction.
Got it.
Okay, so using our values that we were given, we have that the sum of the distances is equal to distance 1 of 3.2 plus distance 2, which is 1.7, plus distance 3, 0.92, plus distance 4, which is 0.35. So this will be the sum of all of our distances. And we know that K is equal to 800. Mu K is equal to 0.28. And M is equal to 5. And we know that gravity is equal to 9.80. So using this and plugging it into our equation, if you plug that into the equation above, you will get a value of X equals 0.46 meters. And this would be our compression, as X is the value for compression. So after the spring is oscillated 4 times, we are able to use the amount of energy lost through each oscillation to figure out how much it was compressed initially. Okay. Any questions on this or anything to add to it, Josh?
No, I think that you covered it pretty well.
Okay. So the main concepts behind this were spring energy and non-restorative forces like friction, where energy is lost regardless of direction. And we were also looking at the concept of work as we were using the work due to friction. So those are some important concepts to know how to apply in problems like this.
Right.
Okay.
So the friction in this case would be one of the from the conservation of energy equation. It would be an example of a work other, right?
Yes.
Right.
Yes. So this would be an example of work other. So our conservation of energy equation is that we have our energy initial is equal to our energy final plus our work other, which in this case was friction. Okay. So
Does
that
it
was
have to be friction?
It doesn't have to be friction. There are other forces. It could be a pushing force. It could be air resistance. Oftentimes it is friction, but it doesn't have to be, no.
So the work other just refers to the work done by anything that is not directly related to the potential energy from a spring, the potential energy from gravity, or the kinetic energy.
Correct, yeah. So anything not directly related to velocity, height, or gravity would be classified as work other. Okay, so if there aren't any more questions on that, we'll move on to our second example. Okay, so okay, so for this second example, we're looking at the energy of a pendulum. So we have a bullet of mass m, which is fired at a pendulum of large mass m and sticks to the pendulum. The pendulum then swings up and reaches a maximum angle theta, what was the initial velocity of the bullet, ignoring air resistance. So what is the first thing that you think we need to look at with this problem, Josh?
Well, it's asking for initial velocity. And initial velocity is, and since this problem is about the energy in this system, we know that the initial velocity is a component of the initial kinetic energy. So maybe we could take a look at that first.
Okay, so looking at energy, so starting with the bullet, I would say that the bullet doesn't have potential energy, but it does have kinetic, right?
Well, wouldn't it have potential energy if it wasn't on the ground?
So for this problem, I'd say just to make it easier, I would set this level where the bullet is passing and where the pendulum is starting at as y equals 0 or h equals 0. That way we can state that anything at the bottom of the pendulum or where the bullet is being fired has 0 potential energy, because mgy or mgh would be 0.
Right, so that works because potential energy is a relative kind of energy, in that, so long, like in both these cases, if we took the initial potential energy of both the bullet and then the pendulum, they'd be equal to each other and they just cancel each other out. So that there's really no point in including them. But once the ball starts swinging on the pendulum and it gains in height, there is a increase in potential energy, and so we can just refer to that increase without actually having to include the initial potential energy.
Exactly. So the bullet has kinetic energy, and as we've set y0 as the path of the bullet, we can say it has no potential. The same concept applies to when the bullet first hits the pendulum. So at the bottom of its swing, it wouldn't have potential, as that is at y equals 0, but I would say it has kinetic as the pendulum is starting its swing, meaning it has some velocity. And at the maximum point of its swing, what type of energy do you think it has, Josh?
Well, at its maximum point, it reaches a stop, similar to when you throw a ball in the air. So that would mean that there's no kinetic energy, so it's entirely potential energy.
Exactly. So potential energy is going to be at the top part of its swing. Now, going back to the kinetic energy of the bullet and the kinetic energy of the pendulum, do you think that all of the kinetic energy of the bullet is transferred into the pendulum at its initial point?
You're asking if all of the kinetic energy is transferred right when it hits the pendulum?
Yes, exactly.
Well, that would be assuming that it's an elastic collision. And we don't know that for sure. Actually, we know it's not an elastic collision because it sticks to the pendulum, meaning that kinetic energy is not conserved. So it means that we can't make that assumption.
Exactly. So because some energy is lost to deforming the bullet when it collides with the pendulum, we can say that the kinetic energy of the bullet initially is not equal to the kinetic energy of the pendulum at the start of its swing. It's not equal. Yeah. So those are a few important concepts to go over. I will move this over to the whiteboard now so that we can do some work. Okay, so we have pendulum and it swings a certain distance. Angle theta. Okay, so we don't know what the velocity of the bullet was, but what we do know is how high the pendulum swings to after it is hit. So we know how much energy is in the pendulum at its final point in the swing, because we know that all that is here at the final point is potential energy. So starting from there, we know that, what is the equation for potential energy?
It would be the mass times the gravitational constant times the change in height.
Okay, so we could call this energy final, because we're using our conservation of energy ideas, is equal to just potential energy. And this is equal to our mass times gravity times our height. Now, as far as mass is concerned, are we just looking at the mass of the pendulum, or are we looking at the combined mass of the pendulum and the bullet?
Well, the problem says that the bullet sticks to the pendulum, and thus it would take more energy to lift that because it is more mass. So we have to make sure that we incorporate both the mass of the bullet and the pendulum into that potential energy equation.
Exactly. In inelastic problems like this, it's important to note when the two objects are together, because you have to account for their combined mass. So m in this case would be little m plus big M. And as far as the height is concerned, because we're looking at a pendulum problem, we know that the length of the string is L. However, how do we find this height? So we know, using our Pythagorean's theorem idea, that we have L as the hypotenuse. And so, writing this out in a clearer way, we have L as the hypotenuse, we have theta, which would give us that the y component here is L cosine of theta. But is L cosine of theta, is that our height?
No, that would be how far down the string, or I guess relatively to the initial position, how far down the string the pendulum currently is. But that's not how high the pendulum is above the ground.
Exactly. So our height would actually be the value of the string below that. So taking the full length of the string, we would get that height is equal to the full length L minus the distance above it, which is L cosine theta. So that would be our value of H in this equation here. So using that, we know that energy final, so the energy at the final point, is equal to M plus M times G times L minus L cosine theta. That is our equation for the energy at the final point of the swing. Now, if we plug in our variables, which we have, we know that big M is equal to 5, little m is equal to 0.2. Gravity is equal to 9.80. Length is equal to 2. And theta is equal to 40 degrees. So this would give us a value of about 23.845 joules. So at the final point in the system, it has about 23.845 joules of energy.
And that is all potential energy.
That is all potential energy, because at the final point of its swing, it will no longer be moving. It doesn't have any velocity, so it will all be potential.
I suppose something important that we didn't necessarily state, but is definitely important for this problem, is we're assuming that this pendulum, the thing it is swinging on, does not stretch like it is swinging on, I don't know, like a metal rod or something. Because if it's stretched, then what kind of energy would be introduced in the system?
Yes. So we're assuming that the string is stationary, basically. It's going to maintain its length of 2 meters and is not going to change. Yeah, so that's how we're looking at this problem.
Otherwise, it'd be elastic energy at different points in the system, which would make it really complicated, because that would change with time, which would really mess up the problem. So it's a nice assumption to make that it won't stretch at all.
Okay. So looking at this, so we know what the energy final is. Now, using our conservation of energy idea, we know that energy final is equal to energy initial. And is there any work other in this problem?
Well, there's no other forces acting on it. So I don't think so.
Okay. So in this case, we can state that energy final is equal to energy initial. So that's it. There's no work other. And we know that energy initial is equal to 1/2 mv squared, as we know that the only energy at the bottom point is kinetic. So that's something we found before. We said that the energy at the bottom of the pendulum is just kinetic energy. So all of the potential is transferred to kinetic. So taking our value of 23.845 joules, which is energy initial, we can state this is equal to 1/2 mv squared. Now we have mass. Now in this case, again, mass would be equal to little m plus big M because the pendulum and the bullet are stuck together. So the variable here that is unknown is velocity at the start of the swing. Now, why do you think we want to know what the velocity is at the beginning of the swing?
Well, if we know that if we know both the mass and the velocity right when it starts swinging, we could then employ our conservation of momentum concept.
Yes, so we want to know what the velocity of the bullet is initially, and using the idea that it's a collision, that would indicate that we're looking at a momentum problem for that part. But momentum is mass times velocity initial equal to mass times velocity final. Now, velocity initial is what we're calculating in this case, but velocity final, how would we get that? Now, velocity final in this case would be the velocity at the beginning of the swing, which would be the velocity in this kinetic energy here. So by using this kinetic energy formula, we can calculate what the final velocity would be in a momentum equation. Okay, so I'm going to clear the whiteboard to have more space to write. So we have 23.845 joules is equal to 1/2 times little m plus big M velocity squared, which using our known equations gives us 1/2 times 5 plus 0.2 times velocity squared. Now, if we save the velocity, if we calculate the velocity, we get velocity is equal to 3.03 meters per second. So that would be our velocity at the beginning of the swing. So that'd be the velocity at the beginning of the swing. So kind of breaking this problem into two parts and looking now at the collision of the bullet and the pendulum. What is our equation for momentum, Josh?
Well, it's pretty simple. It's just the mass times the mass times the initial velocity is equal to the mass times the final velocity. But because we have the inelastic, the mass is increasing. But ends up being little m times v, I don't know, the initial v1, whatever you want to call it, and that would be equal to little m plus big M times the velocity that we just calculated.
Yeah, so we have little m times the velocity of the bullet plus big M times the velocity of the pendulum is equal to their combined mass, because it's an inelastic collision, times velocity, which is the velocity we just calculated. So that velocity would be the final velocity in terms of the collision, but the initial velocity in terms of the swing of the pendulum. So this is why we're kind of looking at this problem in two parts. So did the pendulum have any velocity initially when looking at the collision part of this, the momentum part?
No, it didn't start moving until after the bolt hit it.
Exactly. So we can say that this value is 0, which just leaves us with the little m times the velocity of the bullet is equal to little m plus big M times the velocity of the pendulum at the initial point of its swing, which is what we calculated from the previous part. So plugging in our known values, we get 0.2 times the velocity of the bullet, which is what we're solving for, so what the question asked for, and equals the combined mass of 5 plus 0.2 times velocity, which is 3.03 meters per second. So solving for that, we would get the velocity of the bullet is equal to about 78.7 meters per second. So the key part of this is that first we looked at the swing of the pendulum. So swing of the pendulum. And then we looked at the collision. So we broke this part into two problems. Okay. Are there any questions on that? So the reason that the reason that we have 0 for MV of the pendulum is because we're looking at the pendulum right before the collision, and before it collides with the bullet, the pendulum isn't moving. It's stationary until it's hit with the bullet, at which point it gains energy, it gains kinetic energy. So before that happens, it doesn't actually have any velocity, so we can say that MVP is equal to 0. And going back to the fact that we broke this problem into two parts, the reason that V initial becomes V final is because it depends on which part of the problem you're looking at. So in the case of the collision, V final is when the pendulum first starts moving. In the case of the swing of the pendulum, V initial is when the pendulum first starts moving. So we broke this into two different parts. And depending on the scope of the problem that you're looking at, V initial or V final will change. Okay, do you have anything to add to this, Josh?
So I guess just a kind of more of a conceptual question. What if this was an elastic collision? What if it was not an elastic? How would that change our process here?
So in the case of an elastic collision, the bullet would have ended up going back in the same direction it came from. Some amount of energy would have been given to the bullet, while some amount of energy would have been given to the pendulum. Most likely, the pendulum would not have swung up as far because it would have gained less energy. In this case, you wouldn't be looking at the combined mass if it was an elastic collision, because it would just be the mass of the pendulum individually. And you would have to look at two different situations. You'd have to look at the velocity of the bullet as it leaves the pendulum, and you'd also have to look at the velocity of the pendulum as it swings. So there would be multiple different situations to look at.
Got it. So if how do you know that the bullet would go the opposite direction?
So in this case, the mass of the pendulum is much greater than the bullet. So when the bullet collides with the pendulum, it wouldn't travel forwards through the pendulum because the mass of the pendulum would stop it from moving forwards. Instead, it would be stopped and it would reverse directions just due to the fact that it's crashing into a much greater mass.
Got it. That makes sense. Okay, so at this point in time, we have finished both our examples, and I figured we could use the rest of the time to address any questions anyone had. I know that someone asked questions about components. We didn't talk too much about that. I think we could maybe address that. If anyone has any other questions, we also address that as well. We want to make sure we give you guys as much help as we can. And we finished a little bit early, had a schedule. So we'll use the rest of the time to answer any questions you guys had. So, I mean, I guess we'll get started talking about component stuff, but then while we're talking, you guys can post any additional questions into the chat. We'll try to get to them as well.
Right. So we went over components a little bit when we were looking at the height of the pendulum, but we didn't really address it very much. We can go over it a little bit more. So the idea behind components is that it really kind of goes back to geometry. Oftentimes you're going to need to break things into triangles, and you have some value in the x direction. So this is, and you have some value in the y direction, and you're going to have an angle. So say you want to find the hypotenuse, or like the overall magnitude of a force, which it often is. So let's just put this in terms of forces. You can use your equations. So you could get, so this would be force. So f of x would be equal to f sine theta, and f of y would be equal to f cosine theta. So this just goes back to our geometry and trig stuff. It looks more complicated when you're doing it in terms of forces and momentum and other things, but in reality, if you break it into its right triangle, it'll be easier to see how the different components relate.
Right. Cool. So hopefully that makes things clearer. And when you're trying to balance equations such as like the sum of s equals ma, you always want to make sure you're adding the components that are in the same direction. Just adding an x component and a y component together, because they're vectors, doesn't actually do much for you. Yeah. Someone had a question regarding your diagram, why fx is vertical. It's really depends on the defined axis system. I guess we didn't define that. She could have wrote FA and FB. So it doesn't really matter as far as that. It's more just the trigonometry. So it's always important to check the trig. Like if you see an X, don't always just assume that's going to be horizontal, because that can lead to you being confused and mistaken. Yeah. So someone had a good question earlier about why it is not negative work, because friction is in the opposite direction. And that is something that we were talking about a bit in the spring example, is because the friction is what is called a non-restorative force, right? And friction is always going to be losing energy, and so it will be taken out of the system. And so at any given time, since it's losing energy, the initial energy will be larger than the final energy plus that work. And so while the work is, as Freya is writing, technically we just did kind of a mathematical simplification. Technically it would be the initial energy minus the work done by friction or in another force rather than specifically friction. That would be equal to your final energy. And so we just did an algebraic trick that would make it easier, because negative signs are not very enjoyable. And also because we had, if you remember from the spring problem, we had things in terms of the potential energy at each point. It was good to have the potential energies be independent. Hopefully that answers your question.
Yeah, so with friction, we can always assume that it's either being added to the final or subtracted from the initial, as it is non-restorative. So the signs on friction will not matter as long as you're subtracting it from the total energy of the initial.
And one more point about that spring problem. There was a simplification that we made, which actually answers someone else's question about kinetic and static coefficients of friction. Is the spring wouldn't have to stop at its natural length. It would stop at the point where the force from the spring, which you calculate from Hooke's law, is not large enough to overcome the static friction force, but we kind of just made an assumption that, because that would take a lot of work to solve that. We'd have to check that at every single time that it would stop. And that would just be very complicated. But an example where, that is an example of where there's both kinetic and static, because it's moving while it's kinetic, but then when it stops, the restoring force of the spring would have to be great enough to overcome the static friction force, if that makes sense.
Yeah. So are there any other questions about the examples we've gone over?
Questions? Let me see if any of them have not been answered. So someone asked if each side can have multiple kinetic energies and potential energies, and that is true. The conservation of energy is basically means all energy in a system, in any given system, will always stay constant. They'll have the same amount before and after anything that happens. So you can have like the kinetic energy of 2 cars, right, would be constant, even though there's like 2 different kinetic energies. So it's really about how you define the system that you're looking at.
So it kind of depends on what points. So when we're using conservation of energy, we're just looking at energy between 2 points. So I can say that energy 1 is equal to energy 2. Or I could also say energy 1 is equal to 3. Or energy 2 is equal to 3. So all of these concepts are the same. So that's the idea of conservation of energy. We're picking an initial point and we're picking a final point, and we're looking at what the energy is at each point and saying that it's conserved. But we can look at this at any point along the path of the pendulum or spring or anything else, and it would still be applied.
Right. So another question was asking about an equation solving for multiple unknowns. Well, if you remember back to the spring problem, we actually had several unknowns. We had, potential energy at 4 different locations. We had a friction force, which we didn't know, and we had 4 different distances. The thing that a general approach to that is using substitution, which is what we did without explicitly saying that, is we substituted our equations into one another until we got something that makes more sense and only had enough unknowns. So hopefully that, like keeping that in mind, just using substitution, or another method you can take would be elimination, which you could subtract equations from each other. But hopefully keeping that in mind should help you.
Yeah, and the same concept was applied to the pendulum problem, where you had a momentum equation and you had a conservation of energy equation. So both problems used multiple equations and different variables in conjunction with each other.
Right. And so this will be the last question before we wrap up. We're running out of time here. And technically it's already answered, but I want to make sure we get it so that it can be in the video. Is yes, in elastic collisions, both momentum and energy are conserved. However, in inelastic collisions, only momentum is conserved, because energy, if you remember from one of the equations, work other is in an inelastic collision, that would be the energy lost to damaging the vehicle or whatever is in the collision. It would be lost to like an increase in temperature. It would be lost to the friction. So elastic pretty much never ever happens. It's a nice assumption to make that helps with physics problems, but in reality, it doesn't really happen. It's just ideal. But yeah, so hopefully that answers your question. Right. Okay. So thank you for attending. This has been our fourth virtual session, I believe. And we are still learning how best to do this in a way that is helpful to you guys. I definitely appreciate the participation this time. Thank you for attending and asking questions. It definitely makes it a much more interactive and enjoyable experience for all. We will post this video as soon as we can. Probably not going to be before the midterm, just because that's tomorrow. Yeah, so we wish you best of luck with your studying. And yeah.
Yep. Good luck with all of your studying, and we'll see you tomorrow. Okay, I'm going to stop the meeting now.